Let us solve our next example. X of n is equal to minus a raised to n u of minus n minus 1. Now this is the anticausal sequence. I will show you how it is anticausal. First let us write the equation we have for x of z is equal to sum over minus infinity to plus infinity. Index is x of n z raised to minus n. Now let us put our x of n in this equation. So it will be, we are putting this initially, and minus a raised to n u of minus n minus 1 z raised to minus n. Now this is the discrete unit step sequence, as we have discussed in previous case also, and this is the anticausal, left side of 0. See this. So this is for the label. So u of minus n minus 1. U of minus n means it is on the left side. So it is plus n and it is minus n 0. Let us plot this u of n. So it is minus 1, it start. So it is shifted, minus 1 it is present, it is 1. Now here it is 1, minus 2, minus 3 and so on, it is up to infinity. So minus 1 to infinity. So this is the summation range for this, and for 0 it is 0, and it is 1 it is 0, or 2 it is 0. So it is absent on right side and shifted by 1 unit to the left. So summation limit will change to, we can modify this. So it is minus infinity to minus 1 minus a raised to n and z raised to minus n. U of minus n minus 1 disappears because its magnitude is 1. So it is 1 here. Let us change this summation so that we can use the relation summation a raised to n over 0 to infinity. Okay. So to simplify this, let us substitute n equal to minus m. So this will become x of z is equal to m minus m equal to minus infinity and minus m equal to minus 1, and here it is minus a raised to minus m and z raised to minus of minus m. So very simple substitution. We'll simplify this further, and this will become m equal to infinity to plus 1. Let us take minus outside. So it is a raised to minus m, z raised to plus m. Okay, and if you simplify this further, we'll take m equal to 1 to infinity, will write like this, and it is a raised to a minus 1, z raised to plus 1, and it is m. Same thing we have written. Now we can use the relation, okay, using sum n equal to 0 to infinity, a raised to n is equal to 1 over 1 minus a. So here in place of a we have a raised to minus 1 z. The same term will appear here. So our x of z will be 1 over 1 minus a raised to minus 1 z. So this is the z transform of minus a raised to n. Sorry, it is minus. So this is the minus term. We have minus term outside. Okay. Now we can simplify this further. For region of convergence, so x of z we have minus 1 minus a raised to minus 1 z. We can write like this: 1 over 1 minus z over a. Okay, nothing will happen. Same term is as it is, just it's a modified, inverted. Okay, now when this term will become infinite, for what value of z and a becomes finite and infinite, that decide the region of convergence. Okay, so if you substitute the value of a smaller than z, then what will happen? So that will change the region of convergence. So mod of z should be smaller than mod of a. Okay, mod of z should be smaller than mod of a. The magnitude of z term should be smaller than mod of a. Then this term will become smaller than 1 and it will give us the finite answer. Okay, so this is the region of convergence. So what is the region of convergence? For this is ROC of x of z is mod of z should be less than mod of a. It means the region of convergence is within unit circle, having radius a. Okay, let us draw this. So imaginary part of z. So it is necessary to write every time this imaginary part and real part of z, and this is a. Okay, and mod of z should be smaller than this value. So this is the region of convergence. ROC is mod of z is smaller than mod of magnitude of a. Okay. Our last example is x of n is equal to a raised to n u of n plus b raised to n u of minus n minus 1. So this is two-sided sequence. We have to solve z transform of this and we have to locate the region of convergence for both. So again, this is the different type of sequence we have taken. So each example is unique and we are getting different region of convergence for each example. So from these examples we can understand what is region of convergence and how the region of convergence changes for the type of sequence, for causal, for non-causal and two-sided sequence. So let us solve this example. So we have x of z is equal to sum of x of n z raised to minus n over minus infinity to plus infinity. Okay, let us substitute this sequence. So it is sum of, we'll use bracket for this, a raised to n u of n plus b raised to n u of minus n minus 1. Okay, so bracket close, it is z raised to minus 1. This is our input sequence to find the z transform. Now because of this, the summation limit changes. This is the a raised to n is multiplied by discrete unit step sequence, which is right side, and its limit, its index is n equal to 0 to infinity. And for this, we have seen in previous example, the limit for this is minus infinity to minus 1. So accordingly, we'll rewrite this x of z as sum of n equal to 0 to infinity a raised to n So u of n will disappear because it is providing only the limit. Okay, as its magnitude is 1, it won't be in the equation. Okay, so it is z raised to minus n. This is one summation. We'll make it separate because summation limits are different. So it is n equal to minus infinity to minus 1. It is b raised to n, z raised to minus n. This will also disappear. Now we have to modify this summation limit by substituting. So here only this summation will do the substitution. So put n equal to minus m as we did in the previous case. So this will change to, so it is m equal to 1 to infinity. So it is b raised to minus m and z raised to plus m, and this will further modify to m equal to 1 to infinity, and it's b raised to minus 1, z raised to m. Okay, now we can use, we'll keep this as it is. So it is sum or this 0 to infinity a raised to n, z raised to minus n. So we'll simplify this also. So it is n equal to 0 to infinity. So a z raised to minus 1 raised to n plus, here it is plus, and m equal to 1 to infinity, b raised to minus 1, z raised to m. So by using relation, okay, which relation we are using? So it is sum of or this 0 to infinity a raised to n is equal to 1 over 1 minus a. So here this is the term will appear in place of s, and this is the term will appear in place of a. We'll get two parts. So it is 1 over 1 minus a z raised to minus 1 plus 1 over 1 minus b raised to minus 1 z. We'll further simplify this as 1 minus a, making it positive, z raised to plus 1. So it is 1 over z plus 1 minus z over b. So this is our x of z. Now we have to check for which values of z and a this term will attain, x of z will attain a finite value. Okay, answer should not be infinite. Okay, we'll check it. Now see, if you substitute here mod of z less than a, it will give you infinite answer. So what is the set of values of z to get the finite values? So mod of z should be greater than mod of a, will get the finite values, and in this case mod of z should be less than the values of mod of b. Okay, we'll get the finite answer for these values, such values which values will be less than the magnitude of b. This will give us the finite values of x of z. So this is the region of convergence. Okay, so this is the region of convergence for both summations. Okay, we'll locate the region of convergence. We have two conditions here. The region of convergence has two conditions, a and b. Sorry, just I am making the rough draw to show the concept. So this value is a, and this one is B, and the region of convergence is between this. So it is the imaginary part of Z and this is real part of Z, and the region of convergence is between this. So we have a ring as a region of convergence. So we have to define the region of convergence. So it is the values of should be mod of Z should be less than magnitude of B and should be greater than magnitude of A. So this is the region of convergence. I hope you understood.